We continue the exercises. MCQ exercise 7. For which reaction order does the half-life gets longer as the initial concentration decrease? For order 0, order 1, order 2, or order 0 and order 1, or none of these answers. We know that the T-half depends on the initial concentration we start with when the order of the reaction is order 0 or order 2. And T-half is independent of the initial concentration when the total order of the reaction is 1. So in this table, for 0 order, T-half is equal A0 divided by 2K. For the first order, T-half equal ln 2 over K. For the second order, T-half equal 1 over Ka0. Pay attention. This is the formulas of T-half obtained for a reaction of the type A2 product. As you observed, as the initial concentration of A increase between experiments, T-half increase. For first order, the T-half is independent of the initial concentration. And in the second order, if you did, for example, 2 experiments of a reaction of second order at different initial concentrations, as the concentration of A decrease, the T-half increase. So the answer, for which reaction order does the half-life gets longer, means increase, at the initial concentration decrease, this is T-half for a second order reaction, and the correct answer is C. MCQ exercise 8. Consider the chemical reaction A gives B plus C, and this reaction takes place in aqueous solution. Its half-life is independent of the initial concentration of A. Directly, we can deduce that this reaction is of first order. Is independent of the initial concentration of A, and T-half is equal 1110 minutes. Calculate in minutes the time required for 25% of A to disappear. In this type of exercises, when we want to calculate the concentration of reactant or product at a certain time, I prefer to construct the table of conversion or the table of advancement for the reaction. The table of conversion, I write a table, A gives B plus C. I put all concentrations of A, B, and C at the given times. So at T equals 0, I will suppose that the concentration of A is A0, 0B, and 0C. He asked to calculate the time T, so this time is unknown, required for 25% of A to disappear. What is the meaning 25% of A disappear at time T? That means the remaining of A is 75%. If 25% reacted, so I have 75% remained, since the concentration of AT equal A0 minus the concentration of A reacted. If 25% of A has been reacted, means 75% of A remained. 75% of A remains, so we have 0.75 A0. The stoichiometry minus x, x, x. So if x equal 25% of A0, x is the quantity reacted or the amount reacted. So if we have 25% of A reacted, it's transformed to B 0.25 A0 and C 0.25 A0. Or you can put, for example, A0 minus x, x, x. X equal 0.25 A0. So x equals 0.25 A0 in case of B and 0.25 A0 in case of C. This is the table of conversion, and this table is very important when you want to calculate the concentration of reactant or the concentration of product per time. The reaction in the given that you have is independent of the initial concentration, so the global order of the reaction is 1. The global order is 1. We have to add 1. And in the reaction of first order, THAF is given by the relation THAF equal ln 2 over K. So K equal ln 2 over THAF, ln 2 over 1110. So we obtain K, and pay attention, the unit of K is time minus 1, since the global order of the reaction is 1. For global order 1, the integrated rate law. What is the importance of the integrated rate law? By using the integrated rate law, we can calculate the concentration of A remained at any time t. And for first order reaction, the integrated rate law is given by the relation ln AT divided by A0 equal 180. So ln AT, we need the time t, so AT is equal 0.75 A0 divided by the initial concentration of A, which is A0, equal minus KT. We put K by its value found previously. We cancel A0, so ln 0.75 equal minus 0.000624 times t. Then we can deduce directly the time t, and the time t should be in the same unit of K, so should be in minutes. So the time needed to convert 25% of the initial A is 461 minutes, and the correct answer is D. MCQ exercise 9. The reaction A to product is of first order with a rate constant 0.33 minute minus 1. In this type of exercise, it's not necessary to mention the total order of the reaction. It's not necessary to mention the total order of the reaction, since the unit of K is given in time minus 1. So directly from the unit of K, we can deduce the total order of the reaction. How many minutes will take for a concentration of A, initially 0.13 molar, to decrease to 0.088 molar? By the same way, we can construct the table of conversion. It's very important to construct this table. We have time, reactant, product at T equals 0. The initial concentration of A0 equals 0.13 m. That of the product P is 0. At time T, the concentration of A is given 0.088. It decreases from 0.13 initially to 0.088. So the concentration AT equals 0.088 molar. So what is the concentration of P? The concentration of P, A0 minus X, give X. So the quantity reacted of A, or the concentration reacted of A, is the concentration of P formed. So the concentration of P equals 0.13 minus 0.088. Pay attention for the stoichiometry. If we have 1A to P, so if we have minus X, we have 2X formation. In this case, minus X plus X. The reaction is of first order, so we apply the integrated rate law, ln AT divided by A0 equal minus KT. Ln AT, this relation can be applied at any time you choose in the reaction. It can be applied at time t, at time t prime, at time t2, at time t1. It depends on the time chosen. I use the time t. So ln 0.088 divided by A0, 0.13 equal minus K, which is the rate constant, 0.33 times T. So we obtain that time T by the same unit of K. So T equal 1.18 minutes or T equal 1.2. So the correct answer is A. Exercise 10. The reaction A to products B and C has a rate constant 0.413 liter per mole per second if the initial concentration of A equal 5.25 10 minus 3. Calculate T half. First, from the unit of K, which is in liter per mole, so m minus 1, second minus 1. From the unit of K, we can deduce that the reaction is of second order. And for second order reaction of the type A to product, the T half is given by the relation 1 over KA0, 1 over K given, the initial concentration of A is given, so we obtain T equal 461.2, and pay attention, the unit of T half is in second. So the correct answer is A. Exercise MCQ 11. A plot 1 over A as a function of time for the reaction A to B and C yields a straight line. So this reaction is of second order. If it took 57 seconds for the concentration of A to decrease by 40% from its initial value, what is the rate constant of the reaction? So we have to calculate K. The variation 1 over A as a function of time is a straight line. So this reaction is of second order. We construct the table of conversion or the table of advancement since we have several concentrations at different times. So at time t equals 0, the initial concentration of A equals 0.05 molar, that of B 0, C 0. At time t equal, what is the time given in the exercise is 57 seconds. After 57 seconds, A decreased by 40%. That means 40% of the initial A has been reacted, implies we have 60% of A0 remained. So the concentration after T equal 57 is equal to 60% of A0. So 60%, 0.6 times 0.05. So the concentration of A is equal to 0.03 molar. Now pay attention for the quantity of B and C formed. Since the stoichiometry of A is 1, that of B is 1, that of C is 1, so if A lose X, we have formation XB and X of C, and the quantity X or the amount X that has been reacted is 40% of A0, so we have 40% of A0, 40% of A0, so 0.40 times 0.05 and 0.40 times 0.05. This is the important table of conversion. Why I construct this table? What is the strategy? To solve K, to find K, I have two methods. Or the relation T have to K, or the integrated rate law. And in this exercise, we don't have T half, so we have to use the integrated rate law. So we have to construct the table of conversion. For a reaction of second order, the integrated rate law is given by 1 over T minus 1 over A0 equal KT. This relation can be applied at any time you choose in the reaction, and I will choose the time given 57 seconds. So 1 over the concentration of A at 55 seconds minus 1 over concentration of A0 equal K, which is the rate constant, times the time, which is 57 seconds. So K equal concentration divided by T equal 1 over AT, 1 over 0.03 minus 1 over 0.05 divided by the time 57. So K equal 0.2339. I have to give the unit. I have to give the unit for K. Never write rate constant without unit. The equilibrium constant is unitless, but the unit of small k, the rate constant, is very important. So is equal 0.2339 m minus 1 second minus 1, since this reaction is of second order. So the correct answer is C. Exercise 12. The decomposition of nitrogen dioxide to an O2 gas, to NO gas and O2 gas has a rate constant 0.498 m second minus 1 at temperature 319 degree, and another rate constant at temperature 354 degree. Look, when temperature increase, the rate constant increase. This is a specific characteristic of the rate constant. So this is the variation of the rate constant as a function of the temperature. I can deduce the order of this reaction, since is m second minus 1, so the order of the reaction is 0. The activation energy of the reaction is, we know the activation energy is the minimum energy required for a reaction to proceed. The activation energy is always positive. This is the energy required, the energy needed. So I can eliminate directly the answer C. And the activation energy is in general from tens to hundreds. So how to calculate the activation energy? The rate constant of a reaction depends on the temperature applied. As T increase, the rate constant increase. So we have K1 at T1 and K2 at T2 in Kelvin. Pay attention to transform the temperature from degree to Kelvin, since I will apply the relation. Len K2 divided by K1 equal minus EA divided by R 1 over T1 minus 1 over T2. Or you can write Len K1 over K2 equal EA over R T2 1 over T2 minus 1 over T1. K1 is given, K2 is given. We put K1 and K2 by their values equal EA divided by R, which is equal 8.314 in joule mole minus 1 Kelvin minus 1. 1 of the temperature T2 in Kelvin 627 minus 1 of the temperature T1 in Kelvin 592. Pay attention, the unit of A is the same as the unit of R used, so EA obtained will be in joule. So EA equal this value and is equal 113.7 kilojoule per mole. Per mole, since the activation energy is always in kilojoule per mole. So the correct answer in this case is B. Exercise MCQ 12. The half-life of a first-order reaction is 49.5 seconds. The rate constant. What is the rate constant? This is a very simple exercise. We solve the same type previously. For a reaction of order 1, T-half is independent of the initial concentration, and T-half equal ln 2 over K. So T-half and K have the same units. So K equal ln 2 over T-half equal ln 2 divided by T-half 49.5. So the value of K obtained should be in second minus 1. In second minus 1, 0.014 second minus 1. So the correct answer is B. Exercise MCQ 14. The catalyzed reaction has activation energy and cause the rate constant. We have to fill the blanks. So what is the effect of the catalyst on the activation energy, and what is the effect of the catalyst on the rate of the reaction? First, what is the definition of the activation energy? The activation energy is the minimum energy needed for the reaction to proceed, and the activation energy is constant for a given reaction. The activation energy depends or can be changed only if you add catalyst. So the catalyst decrease the value of the activation energy. Why? Why the catalyst decrease the activation energy? Since the addition of the catalyst will change the pathway of the mechanism of the reaction. So what is the main properties of the catalyst? The catalyst makes some non-spontaneous reaction spontaneous. When the reaction is spontaneous, the addition of the catalyst will speed the rate of the reaction. The catalysts are not consumed in the reaction. This is the case of the heterogeneous catalyst. They are involved in the intermediate step of a reaction. They lower the activation energy. So these are the properties. These are the properties of a catalyst. And if we look to these properties, we can see that the catalyst increase the rate of the reaction and decrease the activation energy. So the catalyzed reaction means you add catalyst to a reaction, has lower activation energy and higher reaction rate. So the correct answer in this case is C.